Question 1. Conformations in isomers with two cyclohexane structures. The first part of this assignment was to work out the systematic names for these two molecules. First, we'll be working on structure A, and I have highlighted the three groups. So you have a benzene ring, a cyclohexane, and a cyanide group. So in this, when you're working out the name, you need to first work out which group will take priority. So this is what we're working out here. So as you can see, highlighted by the orange, you have the benzene ring, and then you have the cyanide group. And in this, because cyanide group is last, the cyanide group takes priority. So you can see the phenyl cyclohexane and carbon nitrile groups, and the phenyl is what you would use at the beginning. At the end it would be a benzene, but at the beginning of the word you'd use phenyl, and then cyclohexane just said as it is, and then you'd use carbon nitrile because the carbon is not part of the cyclohexane, so you'd say carbon nitrile, and that's the cyanide group. And you should not forget the numbers to represent which carbon the group is attached to. When you're working out the number to show where the group is attached to, you start on the priority group. So it'll be 4-phenyl cyclohexane carbon nitrile, and carbon nitrile would not have a number on it. Joining the name together, this is what it would look like. Having done structure A, we're looking at structure B now, and I've circled the three groups that are in this structure. So you have cyclohexane, a fluoride group, and then an ethyl group. Using the same technique to see which group takes priority, we can see that the fluoride group takes priority over the ethyl group. So the fluoride group is 1 and the ethyl group is 2, so you would write it as 2-ethyl, 1-fluorocyclohexane. And it is in alphabetical order, so ethyl comes first before the fluoro. For part B of this question, they asked for the two possible chair conformations and also comment on the relative population at equilibrium. In this section about the conformations of cyclohexane, I'm going to go into a bit of the theory first so I can understand it better. I've drawn out the 4 conformations of cyclohexane here. So you have the chair conformation on the top left, and then the boat conformation on the bottom right, and in between that you have the half chair conformation and the twisted boat conformation. Here is the stability, or a diagram showing the stability of these different conformations. At the bottom, which is almost 0 kilojoules per mole, you have the chair conformation, and way higher you have the half chair, which is very unstable, and that's about 10. Then you have the twisted boat, which goes down a bit, and that's about 7. And then at 8, you have the boat conformation, and it goes back and forth. So the molecule changes shape, and it's called the ring flipping maneuver. And at the bottom, you can see it goes back and forth, which is quite cool. Oh, I've got a video there. In this chair conformation of the cyclohexane, you can see both the axial and equatorial bonds coming off the cyclohexane, and at the ends of these would just be hydrogen if it was a cyclohexane. And the bonds are perfectly separated, which is why it's the most stable structure. And this could be depicted better with the Newman's projection model. You can see the carbons and how they're the same. Maybe that'll make it easier to understand, but you can see they're all staggered, where they're perfectly separated. Looking at the structure A, or the 4-phenyl cyclohexane carbon nitrile, as we've just found out, you can see that both bonds coming off the cyclohexane ring here are coming out of the plane. But all that really matters is that both bonds are going in the same direction, because if you rotated it along its horizontal axis, it would be going away, but it'll be the same molecule. And this means that the groups can only be equatorial for the phenyl, or axial for the nitrile, or vice versa, where it's the other way around. So it cannot be diaxial or diequatorial. These are the two conformations I was just talking about. On the left, the benzene is equatorial and the nitrile is axial. And on the right, the benzene is axial and the nitrile is equatorial. So to find out which one has the highest stability, you really look at the group with the highest steric bulk, and in this situation it'll be the phenyl group, or the benzene, which it prefers to be in the equatorial position, as it interacts less with the groups, or even the hydrogen, but it will interact with the nitrile group far more. And this means that the structure shown on the left is more stable, and henceforth is more populous, so the balanced equation will go more to the right. And this is the reverse symbol, and it would be pointing further to the left than on the right. This is a similar situation with the 2-ethyl 1-fluoro cyclohexane, or structure B, and in this one also the two groups are pointing in the same direction, this time with dashed lines. As I said before, doesn't really matter. So as well in this one, it cannot be diaxial or diequatorial. Now here I've drawn the two conformations with a nice little animation, and on the left you can see that the ethyl group is axial and the fluoride group is equatorial, and on the right the ethyl group is equatorial and the fluoride group is axial. So using the same idea as before, the group with the highest steric bulk, in this situation the ethyl group, with more stable in the equatorial formation than the axial, and this means that the right conformation is more stable, and that's why I've drawn the arrow pointing to the right, which is larger, so be more populous. Going into part C of this question, it asks what is the skeletal structure and give the systematic names for the two structural isomers of the molecule A that are also geometric isomers of each other. When working out the structural isomer of this molecule, the first thing I thought to do was work out the double bond equivalence, and that uses the equation 2C plus 2 plus N minus H minus X, with brackets over that, all divided by 2, and that's basically the carbon, the nitrogen, the hydrogen, and the halide, with the key at the bottom right. And this would work out to be 7 using the molecule. And this means that any structural isomer would contain, at most, a combination of 7 pi bonds and ring structures. We can test this by counting in a molecule above. So you start with 1 pi bond, 2 pi bonds, then you've got 3, 4, and 5 pi bonds in the benzene ring, and then you've also got the ring itself, which is 1, so that's 6, and then another ring for the cyclohexane, and that works out to be 7, the same as the double bond equivalence. And that should be the same in my isomer. This is the isomer I've made, including a double bond, so I can actually make a geometric isomer of itself. And I've circled the three of the 4 groups, including the hydrogen, but you can kind of imagine what that would look like. And I've worked out the MR, or grams per mole, of each of the groups, and this would work out I've included the hydrogen. You can't forget the hydrogen, and that's 1. But you work out the heaviest groups. So this one here, the benzene, is 77, which is far more than the 1 hydrogen. And then you've also got the nitrile group, which is 54, which is far higher than the 29 of the ethyl group. So the phenyl group and the nitrile group will take priority on either side of the double bond. So in this structure here, this will be a cis geometric isomer. Here you can see I've drawn out the 2 different geometric isomers. I've just talked about the cis isomer, and on the right is the trans, and you can see that the benzene group is pointing in the upwards direction. So in the trans isomer, the priority groups, the phenyl group and the nitrile group, are on different sides. So that's why it is a trans. The systematic names would just have the Z and the E before it, as if it was a number. Part D of this question asks us to draw the skeletal structures of the 2 structural isomers of molecule B, and they would be optical isomers of each other. There are 2 chiral centers within this molecule, which means there'll be 4 enantiomers. This does not make it a meso, as there is no line of symmetry between the 2 groups, and the groups are different. Here is the first set of enantiomers that we will be doing. These enantiomers are non-superimposable mirror images of each other, so that's why it's got a dotted line in the middle. It's as if one is seeing the reflection of itself. Also, when working out whether the 2 chiral centers are an S or an R, you start with the highest priority group. In this situation, it'll be the fluoride group and then the ethyl group. And the S would be anti-clockwise and the R would be clockwise. And the other enantiomer is the opposite, as it is the mirror image. This is the other enantiomer. You can see that the fluoride group is going away instead of coming towards us now. The naming for this one would be the either RR or SS. And if I hadn't told you, the 1 and 3 is the carbon that the chiral center is on, so that they just know which one you are talking about. This is a fun diagram showing which of the enantiomers are enantiomers of each other and which one are diastereomers. You can see that the 2 enantiomers are not enantiomers of each other.